Hi class, we continue our study of functions in this lecture by moving in to the topic called transformation of functions. Now this transformation of functions is actually going to be a quick and easy way to sketch the graphs of functions when we make little modifications to them compared to a much simpler function. Okay, so in this lecture I want to get through 5 types of transformation of functions: vertical shifting, horizontal shifting, reflecting graphs, vertical stretching and shrinking, and then finally horizontal stretching and shrinking. Okay. In this section, we study how certain transformations of a function can affect its graph. So this will give us a better understanding of how to graph functions, also how to do them very easily. So we're going to study these transformations of shifting, reflecting, and stretching. Okay, so let's do the vertical shifting. This is the easiest one. So adding a constant to a function shifts its graph vertically. Okay, upward if the constant is positive and downward if it's negative. So in general, suppose you know the graph of y is equal to f of x. How do we obtain from it the graphs of y is equal to f of x plus c and y is equal to f of x minus c? Okay, so either adding a constant or subtracting a constant. So all that happens is the y-coordinate of each point of the graph of f of y is equal to f of x plus c is c units above the y-coordinates of the corresponding graph of y is equal to f of x. So you're just moving the graph up c units. That's literally it. Okay, so we obtain this graph here simply by shifting the graph of the original function y is equal to f of x upward c units. Similarly, we obtain the graph of y is equal to f of x minus c by shifting the graph of y is equal to f of x down c units. Okay, so what you're going to see here in blue is y is equal to f of x. And then in red here, what you're seeing is y is equal to f of x plus c. All you're doing is moving every point of the graph up c units. Similarly, here's f of x. Here's f of x minus c. All you're doing if you're subtracting c is moving it down c units. That's it. So let's use the graph of f of x is equal to x squared to stretch the graph of each of these. We have this new graph x squared plus 3 and this other graph x squared minus 2. So here you're seeing it's a positive c, so you're just going to move the graph up 3 units. Here you see it's negative, so you're going to move the graph down 2 units. Excuse me, sorry about that. Okay, so here, this first one. You're going to see in blue f of x is equal to x squared. All you're doing here for the plus 3 is you're taking each point of the graph and moving it up 3 units to get x squared plus 3. That's in the red graph. Then the purple, x squared minus 2, you're just taking the graph and moving every unit down 2. That's it. That's all you're doing whenever you have a constant tacked on at the end of this graph. Okay, now let's talk about horizontal shifting. Suppose that we know the graph of y is equal to f of x. How do we use it to obtain the graphs of y is equal to f of? Now notice, this is important, inside the parentheses of the function. F of x plus c and y is equal to f of x minus c. Okay? The value of f of x minus c at x is the same as the value of f of x at x minus c. Okay, so this is important. Since x minus c is c units to the left of x, it follows that the graph of y is equal to f of x minus c is just the graph of y is equal f of x shifted to the right c units. So this is going to seem really weird, but when you're inside the parentheses here, it works the opposite way you think. So if you're x minus c, you're moving to the right c units. Similarly, if you take y is equal to f of x plus c, is the graph of f of x shifted to the left c unit. So if you see plus c, you're going to the left c units. All right, so you can see here, in blue here, if we have f of x, if in red here we have f of x minus c. So when you have this minus here, you're just taking the graph and moving to the right c units. Okay, I know it seems weird because it's a minus sign here, but it's to the right c units. Here, if you have f of x is equal to f of x in blue, in red here we have f of x plus c. So I have this plus c inside the parentheses. You're going to go to the left c units. All right, what do I mean by inside the parentheses? Let me show you. So use this graph f of x is equal to x squared to sketch the graph of each of these. So I have g of x is equal to x plus 4 squared, and h of x is equal to x minus 2 squared. So notice that I have the quantity squared. Okay, here I'm taking the quantity plus 4 squared, so it's inside the parentheses. So I have plus 4 here. So what that means, I'm going to take this graph and shift it to the left 4 units. Here I have x minus 2 squared instead of x squared. So I have minus 2. So I'm going to move it to the right 2 units. Okay, so to find g, we shift the graph to the left 4 units. To find h, we shift the graph to the right 2 units. So you can see in blue here, here's the x squared. So I take this x plus 4 squared, I move it to the left 4 units. So it's the same graph, just moved to the left 4 units. Here it's minus 2, so it's the same graph moved to the right 2 units. All right, and that's all you do with these horizontal movements here. All right, let's talk about reflecting graphs now. Suppose we know the graph of f of y is equal to f of x. How do we use it to obtain the graphs of y is equal to, now I'm negating f of x, so minus f of x, and y is equal now inside parentheses f of negative x. All right, the y-coordinate of each point on the graph of y is equal to negative f of x is simply the negative of the y-coordinate. All right, so when you have this case, all right, the desired graph is a reflection of the graph in the x-axis. So it's going to take the graph and flip it upside down. On the other hand, this is where it gets a little bit more tricky. The value of y is equal to f of negative x at x is the same as the value of y is equal to f of x at negative x. Okay, so the desired graph here is the reflection of this y is equal to f of x on the y-axis. Okay, so this one's a little bit easier because I'm just going to take the graph and flip it upside down. Here I'm going to take it and I'm going to reflect it on the y-axis, so it's a little bit more confusing. All right, let me show you. So y is equal to minus f of x. You flip it along the x-axis. So if this is y is equal to f of x, you're going to flip it down on the x-axis here, and this is y is equal to negative f of x. So it's just the same graph, just reflected on the x-axis. Here, y is equal to f of negative x. Here's what the original function y is equal to f of x looks like. So I'm taking it and reflecting it on the y-axis here. Okay, so notice it's like you took it and you rotated it over on the y-axis. All right, let's do two quick examples here. All right, so let's sketch the graph of each of these. F of x is equal to negative x squared. So it's x squared, and then you make it negative. That's important. And g of x is equal to the square root of negative x. So here, the negative sign is outside the function. Here, it's inside the function. It's underneath the radical. So for the first one, A, start by making the graph of f of x is equal to x squared. You see it in blue here. Okay, the graph of f of x is equal to negative x is just the graph reflected along the x-axis. So I'm just going to take this and flip it down here. Okay, so it just rotates along the x-axis. So every positive value became negative. That's just really what happened. Here, you make the graph of y is equal to the square root of x. It's in blue. So the graph of g of x is equal to the square root of negative x. You're just going to take this blue graph and you're going to reflect it on the y-axis. So you're going to flip it over here. And this is what g of x is equal to the square root of negative x looks like in red here. Just got rotated around the y-axis like this. Okay, so note that the domain here, all right, of this new function here is as negative values because a negative times a negative would become a positive. So that's why it's on the negative x values here. All right, let's talk about vertical stretching and shrinking now. Suppose we know the graph of y is equal to f of x. All right, how do we obtain the graph of y is equal to c times f of x? Okay, so the y-coordinate of y is equal to c times f of x at x is the same as the corresponding y-coordinate of y is equal to f of x just multiplied by c. So you're just multiplying the graph by c. Okay, so note here, okay, with vertical stretching. If c is greater than 1, what you're doing is you're taking the graph and you're stretching it. You're pulling it up. You're stretching it, okay? If c is between 0 and 1, it's a fraction, okay? You're shrinking the graph because you're taking the value and multiplying it by a value less than 1. So the graph is going to get pushed down or shrunk. So when c is greater than 1, it's stretching. When c is less than 1 but greater than 0, okay, it's a shrink. All right, so let's do this. So let's use the graph of f of x is equal to x squared to stretch the graph of each function. So I have g of x is equal to 3 times x squared, okay, and then I have this other one, h of x is 1/3 times x squared. All right, so notice that the value c in front of the x squared here is greater than 1, so this is going to get stretched. Here the value of c is between 0 and 1, so this value is going to get shrunk. All right, so for the first one, the graph of g is obtained by multiplying the y-coordinate of each point on the graph of f by 3. Okay, that is to obtain the graph of g, we stretch the graph of f vertically by a factor of 3. All right, so it's the same thing with the other one. For b here, you're going to notice that in blue is b. The graph of h is obtained by multiplying the y-coordinate of each point on the graph of f by 1/3. That is to obtain the graph of h. We shrink the graph of f vertically by a factor of 1/3. Okay? So I'll talk about what they mean by the widest here. All right, so what you're noticing here, first off, in red here, in purple here is the original function, okay, x squared. So when you multiply it by 3, every value is getting pushed up. So it looks like it's getting pushed in, but what's really happening is it's rising faster. Okay, so it's going to get skinnier and taller. Okay. In blue here, what you see is you have the 1/3 x squared. So it looks like it got shorter and wider. Okay, that's because the function's not increasing as fast because it's getting multiplied by that factor of 1/3. All right, let's end now talking about horizontal stretching and shrinking. So we did vertical, now it's horizontal. All right, now we consider this horizontal shrinking and stretching of graphs. If we know the graph of y is equal to f of x, then how is the graph of y is equal to f of c of x related to it? Okay, so the y-coordinate of y is equal to f of c of x is the x-coordinate at x is the same as the y-coordinate of y is equal to f of x at this new value c of x. Right? Thus, the x-coordinate in the graph corresponds to the x-coordinate in the graph of this new function, just multiplied by c, that's it. So looking at this the other way, we see that the x-coordinate of the graph of y is equal to f of c of x are the x-coordinates of the graph of y is equal to f of x just multiplied by 1/c. Okay, so when c is a number greater than 1, okay, it's gonna, this 1/c is a fraction. When c is a fraction, all right, it's 1 divided by a fraction, it's going to become a larger number. All right, so in other words, the change of the graph of y is equal to f of x to the graph of y is equal to f of c of x must shrink or stretch, all right, the graph horizontally by a factor of 1 divided by c. All right, so as long as c is positive, all right, it's summarized in the following box. If c is greater than 1, what you're going to do, you see here in blue, okay, this is the original function, y is equal to f of x. If c is greater than 1, you're going to shrink the graph. You're going to push it in, okay? If c is between 0 and 1, all right, it's a fraction. You're going to, in blue here, you see your original graph. What you're going to do is you're going to take the graph and you're going to stretch it. You're going to pull it apart. So it maintains the same basic shape concept here, all right? Just you're either going to push the graph in like a spring or you're going to expand the graph out like a spring. All right, let's take a look at these two examples here. Okay, so the graph of y is equal to f of x is shown in this figure here. Okay, let's sketch the graph of each function. So first off, this is y is equal to f of x. Okay, it's like this. If I have y is equal to f of 2x, all right, because my c is greater than 1, what you're going to do is you're going to take this and you're going to push it in. It's like compressing the spring. Okay? All right. So this new value, my value of c is 2. So my new x values are going to be 1/c. So basically instead of 1, it's going to be 1/2 here. Okay? Here, y is equal to f of 1/2 x. This is my c, so 1 divided by 1/2 is 2. So this point is going to go from here to here now. It's going to get pulled apart. It's going to get stretched. All right, so first one, you shrink the graph horizontally by a factor of 1/2 because it's 1 over c to obtain the graph in figure 9, see shown there. And as I said in the previous slide, you're going to stretch the graph horizontally by a factor of 2 to obtain this new figure in 10 here. All right, I know there was a lot of rules in here, but if you keep this for reference, you should be able to sketch these graphs pretty quickly.